States of matter. Solids, liquids, and gases are the three states of matter that are most prominently featured here on Earth. The properties of each state differ from each other considerably. Compressibility, solids and liquids are not compressible much at all, whereas gases are highly compressible. Density, solids and liquids have a very high density, gases are very low. Viscosity, which is defined as the resistance to flow, solids don't flow at all, so it's a very high viscosity. Mediums have liquid viscosity, and gases have basically no resistance to flow, very low viscosity. Finally, in terms of potential energy, solids are already in the lowest energy state, so they've got the lowest potential energy. Liquids slightly more, as you have to add energy to solids to make them turn into a liquid, and then you have to add more energy further to liquids to turn them into a gas. Now, as far as viscosity is concerned, the weaker the particle interactions, the lower the viscosity. And remember, water is unique that because of hydrogen bonding, its liquid state is more dense than its solid state. The properties of a material will vary depending on its state. For example, with salt, as a solid, salt is not conductive because its electrons are not mobile. But turn salt into a liquid, NaCl, it will all of a sudden become conductive because now its valence electrons are more mobile. The density of water, of liquid, is 999 grams per liter. Turn into a gas, and the density drops by over 1,000 times. And the viscosity of water, the liquid, it's 0.664, whereas when it's a gas, there's almost no resistance to flow at all. Why is the viscosity of water so much lower in the gas state than in the liquid state? Well, let's take a look at what's going on there. In the liquid state, you have water, O, H, H. Let's put another water there, H, O, H. Because of the strong polarity of these bonds, the hydrogens are partially positively charged, whereas the oxygens are negatively charged. In the liquid state, they get close enough to each other that these hydrogen bonds will keep them closer together. However, once you get to the gas state, the energy to get it to the gas state is such that these molecules become so far apart that the London forces cannot affect them. And so therefore, in this case, as the molecules try and flow past each other, they are held up by the hydrogen bonds. Where in this case, in the gas, those hydrogen bonds really have very little effect, and therefore the molecules are free to flow past without much in the way of interference from the other molecules. As it says here, the Coulombic attractions are much weaker in the gas than in the liquid, so the molecules demonstrate very little resistance to the shearing forces that cause molecules to flow past one another. Now let's talk about solids a little bit. Recall the properties of various solids. Metallic solids have a high melting point. Metals like copper and silver are excellent conductors of electricity and can be bent and drawn so they are malleable. Ionic compounds, because of the strong Coulombic attractions between the cations and the anions, also have a high melting point. However, in the solid state, ionic compounds are not conductive. Only as a liquid are the electrons mobile. Malleable, because of the strong forces holding them together, they can't be bent and their malleability is low. Covalent network, again, because of the strong attractions, the covalent bonds connecting all of the atoms together, the melting point will be very high. Think of a diamond. Conductivity, the electrons are completely bound up in the atoms. Therefore, there is some conductivity, but not very much. The malleability, very low, because everything are bonded, there are no mobile electrons to allow it to bend. Finally, molecules. Molecules are only held together by IMFs. Therefore, their melting point is low. The electrons are completely bound up into the molecules. Therefore, they're not mobile. They are not conductive. And in fact, what we use for insulators, things like wood and plastic, are all molecular compounds. Finally, malleability. Again, there's no mobility of the electrons, so that molecular compounds are not malleable. Liquids distinguish themselves from the solid phase by the ability to flow due to diminished Coulombic attractions between the particles. Hydraulic systems take advantage of a liquid's ability to take the shape of its container, but still have low compressibility to exert a force. See here that you take something that's a high, narrow column, push it down, change the dimensions of the container, now it's wide, and it can be still used to push up the piston on this end. Viscosity of a liquid is influenced by the strength of the Coulombic attractions between particles. So, if we look at the highest viscosity, or where you have hydrogen bonds and not very strong London dispersion forces, like in water. Now, if we look at alcohol, it's got not as strong dipole-dipole forces, but there's some, and it's got some London dispersion forces because it is somewhat polarizable, and it's somewhere there less than water. Now we look at C6H6, benzene, and benzene has very strong London dispersion forces, both because of the number of electrons and the surface area created by the benzene ring. There are no dipole-dipole forces, yet its viscosity is greater than that of alcohol simply because of the stronger London dispersion forces. Note, LDF stands for London dispersion forces, and DDF stands for dipole-dipole forces. The viscosity of motor oil is critical to correct engine performance. Engine oil at ratings indicate the resistance to flow at 0 and at 100 degrees. For example, a 10W40 oil indicates that oil will stay thicker at both 0 and 100 degrees than does oil rated as 5W30. If the oil gets too thin, it will not lubricate adequately, and goodbye engine.